So we were talking about what happens to the Bunsen burner at the tip, because what we found about the flame stabilization was, largely speaking, we are now talking about like the shoulder of the flame, where you have the normal component of the flow velocity tries to balance the flame speed that is normal to the flame itself, and therefore the flame shapes itself corresponding to that. But that is true for most of the shoulder of the flame. But if you now think about what happens to the tip, no matter what the flame speed flow velocity balance is, the tip also always has to actually propagate against the flow directly, right. So which means no matter what the flow speed is and how the flame speed is able to balance that, the tip always has to adjust itself to match the flow speed to the extent it can, right. So question is, how does that happen, right. So what we find is we now have to think about a locally highly curved flame there, and then see what happens when you now have a flame that is so curved out there. And therefore what we want to do is think about flame curvature, and also another aspect of it that we need to worry about called the flow divergence effect in the context of a small perturbation to a plane flame. So if you now begin to think about a nominally plane flame that is propagating with a flame velocity SL superscript naught, alright, which means in a flame fixed coordinate system you have your reactants, unburnt reactants coming into the flame at SL superscript naught. Then let us now think about what happens when you now perturb the flame about this point, okay. And this particular picture here shows a couple of things. One is you have one part of the flame that is curved convex against the incoming flow, and the other part of the flame is curved concave relative to the incoming flow. We need to think about what happens to these two parts separately, but we should probably come to the same conclusion either way. So typically in the classroom, if you explain what is happening to the convex part in the exam, you can expect a question of what happens to the concave part, right. So you should be able to think about this just as well. What we want to talk about here is actually two different kinds of processes that come about when you have this kind of curvature. One is a thermal thermodiffusive imbalance, or balance or imbalance depending upon what really happens. So one of the things that happens is when you now have a flame that is curved, let's now take the concave part. This is a little bit more intuitive, and it's also kind of like what's happening in the Bunsen flame tip, so this is pretty instructive. When you're now thinking about a curvature which is now beginning to be of the order of, not exactly equal to, but of the order of, which means still a little greater than the flame thickness, okay. Now so keep in mind what is meant by flame thickness. The flame thickness includes the preheat zone and the reaction zone, and the preheat zone is where the upstream heat conduction and downstream species diffusion happens, along with convection superposed on for both the species mass as well as the enthalpy. What we are now beginning to see is, if you now have a curvature like this, then beyond what is being heated up for the cold reactants, you now have a focused effect of heating the reactants. So this conduction now becomes multidimensional, the heat conduction becomes multidimensional, and therefore you are now actually heating the reactants significantly more than if the flame were planar. This should actually give rise to a tendency for the flame speed to increase, alright. Now on the other hand, look at what is happening to the species diffusion. The species diffusion now is going to actually go radially outward. So typically when you are looking at something like a fuel lean flame for example, then the diffusion species, so the diffusion reactant is fuel in a fuel lean situation, and when you are now trying to have this so that it is more critical to think about the deficient reactant. So the deficient reactant now spreads thinner across in a radially outward manner. So instead of actually feeding a planar flame straight, it is actually spreading itself thin. That means the flame is running out of the deficient reactant more than in the case of a planar flame if you have a concave curvature relative to the upstream, right. So this has a tendency to decrease the flame speed, alright. So you now have a possible balance between these two effects that will tell you whether the curvature is going to stay or grow or decay. So when you now have to think about a balance between heat conduction and species diffusion, what comes to our minds? It's a Lewis number, right. So we have to think about what the Lewis number is, and depending upon what the Lewis number is, okay. So if you now have a Lewis number that is greater than 1, right. So if you now have a Lewis number that is greater than 1, that means the heat conduction upstream, right, is more than the mass diffusion downstream, right. That means the species depletion effect is not going to be as significant as the focused heat conduction, which means that the flame is actually going to propagate more vigorously, or there is going to be a net effect of increase in the flame speed, alright. So if you now think about what is happening at the tip of the flame for a greater than unity Lewis number, right, we expect a more intense burning, an increased flame speed that can try to match the flow speed there, alright, for a greater than Lewis, greater than unity Lewis number. But if you now have in the Bunsen burner tip, right, the Bunsen burner tip for LE less than 1, you now have a greater extent of deficient species depletion that is happening when compared to the extent of upstream heat conduction. So the flame is essentially running out of reactant even if it is trying hard to conduct heat upstream to heat up whatever is remaining of the reactants. So this leads to, this could lead, okay, so could lead to a local flame extinction, alright. Now many times, I shouldn't say many times, sometimes you do see flames which have a hole in the middle. So that means you now have a flame that keeps going up like this, instead of turning around it actually goes up like that, and see that I am actually drawing it with a lighter line. That's simply because the flame fades as it goes along, that indicates like a lesser burning intensity progressively and the extinction there, alright. So you now have a hole in the flame. It's not as if like you need to have LE less than 1 for this hole in the flame. There is also one more thing that we have to think about. So the first thing that we talked about was the thermal diffusive imbalance, thermal hyphen diffusive imbalance. The second thing that we have to worry about is the density jump, okay. So density density jump across the flame. So what is the consequence of having a decrease in density for the products relative to the reactants when the flow gets past the flame, right? Any ideas here? What's going to happen? if the flow now tries to go past. So we try to still go through the same idea, that is you now have a nominally flat flame with a SL naught, but then now you are beginning to think about the fact that the density of the products is going to be less than the density of the reactants and perturb the flame to be non-planar. Alright. So as a consequence of the density difference, local mass balance dictates that the velocity should compensate for it. Alright. So if you now think about a point here along a curved flame, what we are basically saying is you now have a, let us suppose that your this is your U naught, and what you want to do is try to decompose this as parallel and perpendicular to the flame, right. So this is U n naught and this is U t naught, and what happens is when you try to have a flow that is going past the flame, it's mainly the normal component that suffers the expansion, because that's how we are normally thinking about a flame. So if you had a unperturbed flame with a flat profile, then what you're basically saying is the normal component of the flow is going to actually expand, right. So what we then have to expect is we need to have the normal component increase significantly. This is significant because what we are talking about is a constant pressure, more or less a constant pressure system, alright, and you have to think about what's the density change because of. The density changes because of the temperature change, so the temperature rises, therefore the density falls, right. So what's the temperature rise like? So if you take like a 300 K over here, and let us say it's reasonable to expect something like a 2400 K there, right. So that's about a temperature rise of about 8-fold, can be 2100, 2400, 2700. Okay, think in terms of factors of 3 or 300 for the sake of simplicity, right, or 3000. So you are now talking about a factor that's somewhere between 7 to 10 times more, alright. So this has to be significant, and then so the density correspondingly decreases, right. So P equals rho RT, and as T increases rho has to decrease, and then rho naught U naught is equal to rho infinity U infinity, or more specifically in this case rho naught U n naught should be equal to rho infinity U n infinity, right. So if rho naught over rho infinity is going to be about a factor of 7 or 8 or 9, then U n infinity is going to be that much higher when compared to U n naught, right. So it would be okay if we extended this line even more, like this particular curve that I drew was only about 3 times, so let's just exaggerate a little bit more, or it's still not an exaggeration, and so this should actually be your UN infinity, right, and the UT naught gets preserved as such when you now want to locate your UT infinity, because that doesn't really suffer any expansion. And then so what happens to the resultant? So the resultant now obviously gets tilted more towards the normal of the flame, alright. So this is basically then your U infinity. This is the picture you would like to see. So what essentially is happening? It essentially means that if you now have a streamline that's coming like this, it's going to get compressed, right. So if you have a streamline that goes like here, it's going to go together, but obviously streamlines can't hit each other, right. They try to turn, and in trying to turn and accommodate each other, they try to disturb the streamlines that are approaching the flame as well, okay. So you now get into a situation where your streamlines should actually turn out to be in reality somewhat like this. It starts bending outward in anticipation of having to converge again further down, right, and correspondingly if you now look at this kind of a curvature, which is what is pertinent for us in a Bunsen burner tip, right. So we expect that the flame should actually increase, sorry, the flow should actually increase or diverge and then converge back again. I am sorry, made a mistake. Right. So look at what's going on here. You have a situation where you are thinking that you want to have a flame that is stabilized at SL naught, right. Now this is what is equal to U locally here. That means you always, this is very important, I think I mentioned this earlier, the way we always want to think about flames, and I will reiterate this when we are dealing with triple flames after doing diffusion flames, the way we always want to think about a flame propagation speed is always relative to the flow speed far upstream of the flame. That means you don't want to worry about all this mess, you have to say it all depends on, it all boils down to how much do I have to open the valves for my flow to actually set in so that the flame is approximately stabilized. What is meant by approximate is it is stationary there, I can actually have a flame fixed coordinate system, what it is doing within the flame fixed coordinate system is not of concern to me so long as it is there, right, and what is the flow speed at which it is there is what is the flame speed is what I would like to think about, right. So if I want to now say that this is what it is, then what is the problem that is happening near the flame? You now find that the flow is locally accelerated when you now have a flame that is curved concave relative to the far upstream reactants, alright. So what has essentially happened is the flame has now induced the flow to go faster at it when it tries to have a concave curvature, right, and this means the flame needs to actually try to compensate for a higher level of increase in flame speed, which should be by a mechanism that we talked about here if it has to survive. If not, it is going to actually cause a local extinction, right. So we see this actually happening in a Bunsen burner. For example, when you now talk about a streamlined path that is approaching the flame, you now know for a fact that you now have a streamlined path that goes like this. So you do have a flow that is actually getting diverged for most part, and then that continues to happen over here, but locally it tries to actually squeeze in and then diverge. So effectively what happens is you need to have to take into account the effect of flow divergence on the planar flame speed. So if you want to think about this effect, you want to try to actually bring this into modifying the planar flame speed such that all this is like a black box, and if you now had a planar flame speed, how is it going to be modified in a way that will take into account the local flow deceleration or acceleration, alright. So there is a way by which you can do this. I am not going to derive this, it's quite beyond the scope of this particular course, but we will just state these things. So if you now assume constant properties, the flame speed is modified as SL equals SL naught minus SL naught script L kappa plus script L n hat dot divergence or n hat dot gradient v vector dot n hat. So here the SL naught is basically the unstretched flame. It does not suffer from the flame curvature and flow divergence effects, okay, but SL is actually the flame speed that you would have to use for a flame that is curved and also induces a flow divergence correspondingly, and therefore alters the flame speed as well, right. So here kappa then is the flame curvature, right. So that's equal to divergence of n hat, which is nothing but negative of divergence of grad g divided by mod grad g in the framework of the G equation. And so of course you can now try to do a chain rule differentiation here. So this is del square g divided by mod grad g plus grad mod grad g times grad g divided by mod grad g squared, which is minus del square g plus n hat dot grad mod grad g divided by mod grad g. Keep in mind we are actually trying to find the flame shape, okay, and the flame shape is now contained in the flame speed, okay. So previously we were trying to find the flame shape based on the unstretched flame speed, right, but now we have to use a stretched flame speed which depends on the shape, and the shape depends on the speed. So you will have to do an iterative solution of this, and it's possible, and there are solutions that can be made available for these things. L here, the script L is what is called as the Markstein's length, and recall I kept talking about a length scale that is of the order of the flame thickness but not exactly equal, so it's somewhat greater, okay, it's a little bit greater than the flame thickness, because if you now have a flame curvature, the heating effect is going to be felt a little bit further upstream than the original unstretched flame thickness, okay. So previously the unstretched flame thickness contained the preheat zone, but now if you curve, like let's say concave, the heating is going to be felt further out, right. So that's kind of like the Markstein's length we are talking about. So it is a quantity of the order of the flame thickness and of course we know that the flame thickness delta depends on the flame speed. This we did long ago, right. So the first time we started talking about the structure of the premix flame, the mass balance in the preheat zone resulted in something like this, okay. But here keep in mind this delta is actually for the stretched flame thickness, the SL is actually the stretched flame speed, okay. And what we are now saying is this depends on L, okay, and so how does L depend on the delta? So there is a derivation for this again which we won't go through, but I will just state for large activation energy of a one step chemical reaction, right. So within the framework of assuming a one step chemical reaction with a large activation energy for it, L over delta, script L over delta is 1 over gamma natural logarithm 1 over 1 minus gamma plus beta Lewis number minus 1 divided by 2 1 minus gamma divided by gamma integral 0 gamma divided by 1 minus gamma natural logarithm 1 plus x divided by x dx. Evidently x is a dummy variable of integration from 0 to gamma over 1 minus gamma. Gamma is now not the ratio of specific heats that you are used to in gas dynamics. This is actually the ratio of temperatures, which is basically a temperature difference divided by the initial temperature, and beta is our Zeldovich number. So it's EA times Tf minus T naught divided by RU Tf squared. So you can see that gamma is actually embedded in here. You could say Tf minus T naught divided by T naught is gamma. So E over RUT RUTF times gamma would be your beta. Now typically it's found that typically L over delta is 2 to 6. So there are analysis. So what you will see is now if you want to try to actually find a curved flame shape, it's quite difficult. It's getting more involved. Your Mach chain's length depends on the flame thickness. The flame thickness depends on the flame speed. The flame speed depends on the Mach chain's length, and so on. So there is like a loop within a loop that's going on here, which we have to solve iteratively. There are analysis where we would just assume a constant Mach chain's length. Let's not worry about. So you pick a number between this because it's about a variable that varies within this range. So let's not worry about it, is the attitude for those analysis. So then what happens, as I said, you see as the flame speed increases, if you now go back to the tip of the Bunsen burner, that's what we were concerned with. If you now keep on increasing the flow speed, right, as it is, the flame speed in this case, the flame speed for the unstretched flame is less than the flow speed, okay, and the flow speed, or put another way, the flow speed is actually greater than the unstretched flame speed, and at the tip, because you now have a concave curvature, the flow tends to actually converge and actually increase faster, flow faster. That means the flame speed has to increase much more to counter that, and that would be through the thermal diffusive imbalance. Alright, and that is obviously possible mainly when you have a Lewis number greater than 1, but still since this effect is countering that, even when you have a Lewis number greater than 1, you could have conditions of local extinction, right. So as the flow rate is progressively increased, right, the flame shoulder adjusts its orientation, but the tip can't. The tip always has to stay as the tip. It can't adjust its orientation to the flow velocity. Therefore, this results in local extinction regardless of LE, whether it's greater than 1 or less than 1, and so on. Fine. What next? We talked about the Bunsen burner. We realized that at the shoulder of the flame, the flow normal component of the flow velocity should match the flame speed for the flame propagating perpendicular to itself. Then we realized that that's not as simple a situation as the tip, so we went through what we needed to go through to think about the tip, and we found that it is not so straightforward. You have to worry about these effects, two effects, mainly the thermal diffusive imbalance and the density variation effect, density change with temperature effect. So all these things are involved in explaining what's going on with the tip. But what about the base? Right? So what's going on at the base? When we did the G equation, we made an assumption that our zeta should be equal to 0 at R equals capital R. That was like a boundary condition that we had adopted, okay, basically saying that the flame is touching the rim of the burner. Of course, within the framework of the G equation, we don't bring into effect the thickness of the flame, alright. So it's as if like the flame is having a thickness, and we are basically saying that the SL is a constant, it doesn't change, and therefore we don't have to also worry about a varying thickness of the flame near the base, and or a varying flame speed as we approach the base, right. But none of these things is true. So we need to now focus a little bit more on what's happening near the base and see what is the fate of the flame speed as we approach the base, as well as the flow isn't uniform either, right. So we tend to think that you have a uniform flow that's approaching the flame, and you have a uniform flame, a constant flame speed with which the flame is trying to attack the reactant flow, and therefore you have a shape. But that was not the case for the flow as well. The flow wasn't uniform there. It is coming out of a burner and it has to satisfy no slip boundary condition. That means the flow velocity has to start from 0, right. So we tend to begin to think, wait a minute, if you are going to have a 0 flow velocity there, that means the flame should be able to propagate against the flow right there along the walls and never really be stabilized above the burner. On the one hand, it looks like the flame has to actually not be held at the burner at all and maybe get pushed up by the flow, but if you now begin to look at the flow, right, it looks like the flame has to go deep in. What's going on, right? So this idea of having to look at the base of the flame takes us to what the issue of what's called as flame stabilization. Flame stabilization. So this refers to the fate of the flame base. Flame base or flame anchor point. Flame stabilization can also be referred to as flame anchoring, because the base is the one that is actually holding the flame. So correspondingly you can also use the term flame holding, right. So flame holding, flame anchoring, flame stabilization, all these things refer to pretty much the same, and it deals with the fate of the flame base, because the base is where the flame is held, right. So we need to look at, so what we just said was we need to look at SL and U variation as you approach the burner rim. Approach the burner rim, right. So let's look at the flow velocity variation, that's simpler. So flow velocity U, okay. So what we expect is if you now have a burner, we have a no slip boundary condition, alright, and of course you could quibble saying we don't know exactly how the flow was formed and where and how is it developing, as it reached a fully developed profile, do we have an entrance length associated with it and so on. Those things are not very relevant, okay. So even in a worst case where you assume like a fully developed flow that is emerging out of the tube, right, and we are talking about laminar flames. So we are looking at a laminar flow, laminar fully developed flow that's coming out of the tube. We expect a parabolic velocity profile, right. But what matters to us is what's happening here, right. So this basically means that we are looking at now what we drew as a line has suddenly become not a thick block. I'm even exaggerating and going further into saying that this is almost like a semi infinite solid filling one quadrant, and with the corner here corresponding to that burner rim, and the flow velocity is locally linear. That's your U. So when we said that we wanted to look at the flame speed and the flow velocity variation as you approach the burner rim, we picked the flow velocity because the flow velocity is always going to be somewhat linearly increasing from the rim inwards towards the center of the tube. So that is more like a monotonic variation. You increase the flow speed, the slope is going to increase. If you decrease the flow speed, the slope is going to decrease, that's all, right. So there is no there are no counter effects or competing effects here, but that's not the problem that's not the case with the flame speed. There are competing effects that we have to worry about for how the flame speed changes as it approaches the rim. So it's not so straightforward, so we consider that next. So how does the flame speed behave, right. There are two factors, in fact two contravening factors that we have to think about. One, first and foremost, as a matter of fact, is the heat loss to the burner. Heat loss to the burner. So when you now have a flame that is approaching the burner, so think about what's happening. If you now have a burner rim that's looking like this, when you're now trying to zoom in into the burner so much, right, you can't simply draw a flame like a single line anymore, pretending that that is going to now contain both your preheat zone and the reaction zone and all those things, right. You now have to worry about how does the preheat zone look like, how does the reaction zone look like. What I know for a fact is far away from this burner rim I'm going to have a certain thickness for the flame, and the preheat zone is going to be thicker than the reaction zone, larger the activation energy, okay. But what happens as you now progressively come closer to the rim is, keep in mind that this is actually the region where the temperature actually rises from the initial temperature to the flame temperature as we go along, and this is the region where most of the conduction is happening. But as you now come down to the flame, the burner rim, you now have a heat conduction that's going on inside the rim as well. So it's suddenly like the burner rim intruded into the preheat zone, because the preheat zone essentially is part of where the conduction happens, right? But the preheat zone was supposed to actually heat up preheat, right? So preheat means it's supposed to heat up the reactants to react. So there is no point in heating up the burner rim, because the burner rim is not hopefully going to react, right? It's kind of like the joke about whether so how does the combustor work? The combustor burns. That's not good news, because the combustor burns means the combustor is not going to be there. So similarly, you don't want to have the burner be part of the reactions, right? So what then happens is, you now essentially are thinking about a thickening, progressively thickening preheat zone, and the fact that we are talking about a heat loss is because the reactants are not the only ones that are getting heated up. Okay, in an adiabatic flame there is a heat transfer going on. It's not as if like there is no heat transfer going on in an adiabatic flame, but it is kind of like, you know, the father gives his money to the son and the son gives the money to the grandson and so on. The money is kept within the family, right? It's not going away. So it's like the reactants are the ones that are actually getting the heat and reacting in the flame. So long as the reactants are the ones that are going to get all the heat and then react in the flame to release that heat, it's an adiabatic system. But the moment the reactants are not the ones that are going to get heated up anymore, that's not an adiabatic system. So obviously then the local flame speed should decrease, right? So the flame essentially becomes a lot thicker, and the flame speed progressively decreases towards the as the flame is held closer and closer. So it's essentially the heat loss to the burner basically means that closer the flame base is located to the burner rim, right, more the heat loss, and SL decreases more, right? The decrease in the SL is more. What we are basically thinking is, as you now have a burner and you are now trying to increase the flame speed, we are beginning to imagine that the base is not exactly touching the rim anymore. The base of the flame is now going to go up a little bit and try to adjust its position. Why would it adjust is something that we are going to see pretty soon, right? But the moment we now begin to think that the flame is not going to be at the rim and can move up or down relative to the rim, what we are basically saying is, closer it is to the rim, more is the heat loss, and therefore the flame speed near the rim is going to be progressively less. So this is a contribution that is going to decrease the flame speed. Okay, the second, decrease the flame speed more and more when the flame is closer to the rim. Second is the mixing with the ambient. Mixing with the ambient, right? Now for the purpose of what we are talking about, let's fix the ambient as air, right? Air as in what we find on earth here, right? That means you now have the oxidizing ambience, right? And then think about what happens as you now allow for mixing to happen. So essentially what this means is, you now have more and more standoff of the flame. Let's say the flame is now further out, okay? So if you now have a flame that is progressively further out, and for this purpose it's sufficient for us to just draw a line to represent the flame. Let's not worry about its thickness, right? It is thicker and so on, that's fine, but what you're looking at is this distance. More this distance, greater is the mixing of the reactants with the ambient, right? What's the consequence of this for the flame speed? That's really the question that we have to ask. That depends on whether the flame is a fuel rich flame or a fuel lean flame, right? So if it were a fuel rich flame, right, so let's just record this: greater the standoff distance, right, more is the mixing. And the question is that mixing going to be increasing the flame speed or decreasing the flame speed, right? So that depends on whether the flame is going to be fuel rich or fuel lean. So fuel rich flame in an oxidizing ambience, what happens now? This region actually becomes closer to stoichiometric, right, because it is a fuel rich flame, and then you are now sending in more oxygen from the side, and therefore it becomes closer to stoichiometric. So this leads to an increase in flame speed, right, with increasing standoff, right, and this goes in the same direction as what the heat loss effect was. In the case of the heat loss, what we understood was the closer the flame is to the burner, lesser is its flame speed, or conversely, the farther it is from the burner, it's going to have a higher flame speed because of less heat loss. This is exactly what we are saying here. Increase in the flame standoff means a increase in the flame speed because it's fuel rich. So in this case this is a little bit more complicated, and we will talk about this later on. What's important for us is to look at a competing effect, that means an opposing effect, right, and that is presented in the case of a fuel lean flame. So in the case of a fuel lean flame, you are already fuel lean, and a greater mixing with the ambient is going to dilute the flame further and further, right, and that means the flame speed is going to decrease as the flame standoff distance increases. The heat loss was less, so the flame speed doesn't have to decrease that much more, but it's going to decrease because of the dilution, right. So dilution decreases the SL with increase in standoff, right. With these two we should now be able to tell how the flame is stabilized. We will do this now, and we will worry about pushing the limits on this to lead to a flashback or a blow off later. So essentially what happens is, if you now have a, let's now put these two together, that means originally if you now had a flow velocity that was locally linear, right, and let me now consider the flow like this, right, that's a flow velocity u. What we are looking for is, if you now have a flame that is like this, let's look at how its flame speed is going to be. Right, as it is over here with respect to like the free stream velocity, the flame speed is low, but the flow speed is actually decreasing linearly, and the flame speed is decreasing because of heat loss on the one hand as its proximity to the burner is determined, and because of the mixing, and we are now considering a fuel lean case. Right. In a fuel lean case, it's a more straightforward for us to think about. So there is a position, there is a condition when maybe the scales aren't good here, so let's consider a scale that looks like that. So there is a condition when the local velocity and the local flame speed match exactly, where you have this curvature facing the flow, right. So this is where you now have a U equals SL. I am not saying U bar equals SL naught or U naught equals SL naught, okay. I am saying U is equal to SL. So this is the stabilization condition. Right. Now what happens when you now try to actually have a flame that is perturbed inward is it now gets closer to the flame, right. So its SL actually becomes less than U because of a greater heat loss effect, alright, but the mixing is not much, so it's not trying to decrease the SL a lot, but the heat loss is actually trying to decrease the SL, and therefore the flame gets pushed backwards to this point. But if you now try to actually have a flame that is pushed further out, it now becomes a lot more extended. You can see how I am drawing these pictures. You now see that it is actually stopping somewhere here, it's stopping here, it can extend further because your mixing fan is more. You now have the reactants reaching a greater distance laterally outward, right. So you can have a flame over here, but in this case the SL actually now becomes greater than U because you don't have too much of a heat loss effect, and therefore it has a tendency to move upstream. You now have a larger flame because the reactants have actually fanned out and they have less heat loss, and they have a tendency to move against a linearly decreasing velocity until you reach a matching point, okay. So effectively it now becomes a local match between a varying flame speed and a varying velocity. The flame speed is not uniformly varying, the velocity is linearly varying, and this match is what is going to actually dictate how the flame is stabilized locally there, and therefore correspondingly a flame standoff distance. Stop here.